Good day, students. Welcome to Mathgotserved.com. In this clip, we're going to be going over problems 1 to 3 of the PARCC Geometry Practice Test. If you want to download this document, feel free to click on this link right here below to gain access to this document. All right, let's take a look at question number 1. Oh, yeah, we have a message here from Naruto. It's giving you thumbs up and saying you can pass this exam. Okay? All right, so problem 1, it says the figure shows triangle ABC is similar to triangle DEF with the side lengths as indicated. What is the value of x? Enter your answer in the box. All right, so here we're dealing with a problem that's testing your understanding of similar triangles, okay? So if triangle ABC, and you have the symbol, and then triangle DEF, what does this mean? This is telling you that these two triangles are similar, okay? So in word form, triangle ABC is similar to triangle DEF. So what does it mean for two triangles to be similar? Two triangles are similar if corresponding angles congruent, okay? If corresponding angles are congruent and the ratio of corresponding sides are in proportion, okay? So let's go ahead and write down that remark real quick. If triangle ABC is similar to triangle DEF, then we have two conditions. Condition number 1, corresponding angles are what? Congruent. Okay? And then condition number 2 is that the ratio of corresponding sides, ratio of corresponding sides are in proportion. Okay? All right, so what does it mean for corresponding angles to be congruent? That means the angle here that corresponds to the angle here are exactly, they have the same measure, okay? So how do we know which angles are corresponding? Now, please do not use the diagram to try to figure out what the corresponding angles are. You want to let the letters guide you, and the order of the letters are very, very important, okay? So A and D are the first letters for the two triangles, so that means angle A is corresponding to what? Angle D in the second triangle, okay? And then angle B in the bigger triangle, this angle is corresponding to which angle here? Angle E, okay? So you see the order, angle E, because that's the second letter. And then angle C is corresponds to angle F. All right, so angle C corresponds to angle F. All right, so that's the accurate order of correspondence. Now we're going to talk about part 2, which is the ratio of corresponding sides are in proportion. Now the best way to figure out which sides are corresponding is to follow the order of the letters again. Okay, so we have triangle ABC, and then we have triangle DEF. Okay, triangle DEF. All right, so what can we talk about concerning the ratio of corresponding sides? Now, side AB is corresponds to side DE. Okay, let's go ahead and write that down. AB, side AB, corresponds to side DE. You see how we're following the order? What's the next pair of corresponding sides? Side BC corresponds with side EF. Okay, so we have side BC, change the color there, side BC corresponds to side EF. And then lastly, side, you can go from the first to the last, AC corresponds to side what? DF. Okay, so let's go ahead and write that down. Side AC corresponds to side DF. So this is another set of information that we can determine if two triangles are congruent, similar. Okay, so these are the corresponding sides. They are in proportion. What does that mean? That means that the ratio of these pair is equal to the ratio of this pair, and it's equal to the ratio of this pair. Okay, so these are the corresponding sides. If these triangles are similar, AB divided by, so AB over DE is going to be equal to BC over EF, and that's going to be equal to AC over DF. Okay, ACDF down here, the pair at the bottom, BCEF, the second pair, and then ABDE as the top pair. So these ratios are in proportion. This is what it means for two triangles to be similar, apart from the fact that corresponding angles are congruent. This is what we need to solve the problem, okay? So in this problem, we're looking for the value of x, which is CB, okay? So we want to find x. Let's write that down. We want to find x, which is equal to CB. So what we're going to do is we're going to pick the ratio that has CB or BC. CB is the same thing as BC. We're going to pick out that ratio, and then we're going to pick another ratio that we know the measures of the bigger triangle and the smaller triangle, okay? So BC and EF will pick this ratio, and if you look at the two triangles, you find out that we know every other side apart from BC. So it doesn't matter what pair we pick, okay? So we can pick these two right here to solve for BC. Okay, so since these triangles are similar, we know that BC over EF is equal to AC over DF. If we put in the values of the triangle in there, BC is X, that's what we're looking for. EF is 5. AC on the big triangle is 27. And then DF on the small triangle is 9. All right, so we have this ratio, this proportion. Now we can solve for x. How do we solve for x here? We just solve this algebraic equation. Now we can simplify the right side. We have x over 5. What is 27 divided by 9? That's 3, right? And then to finish this up, we simply multiply both sides by 5. So your final answer is x equals 15. Okay, and that's that. All right, let's take a look at problem number 2. It says the figure shows two perpendicular lines, S and R, intersecting at a point P in the interior of a trapezoid. Lines R is parallel to the bases and bisects both legs of the trapezoid. Line S bisects both bases of the trapezoid. This transformation will always carry the figure onto itself. Select all that apply. So this is another question where you might have multiple answers that are correct. All right, so what does it mean for a transformation to carry a figure onto itself? If a transformation carries a figure onto itself, that means after the transformation, you end up with exactly the same image, an identical copy of what you started with. Now, one shortcut for transformations carrying a figure onto itself is a line of symmetry. Okay, if a line is a line of symmetry on a figure, then reflection along that line carries the figure onto itself. Okay, so let's just note that on the side. Reflection along a line of symmetry carries a figure onto itself. All right, so let's keep that in mind. So if you look at these two lines, which of them is a line of symmetry? Which line divides this figure into two identical parts? Or think about it. If you fold this paper along these lines, which one will you have two identical pieces? If you take S, take a look at S. If you fold this, you notice that these two will fall on top of each other. These two vertices will fall on top of each other. Line S is a line of symmetry. So what does that mean? If you reflect along that line, this figure will be carried upon itself. Okay? So what happens when you reflect along the line S? This portion right here gets reflected there, this gets reflected there. So let's look at the options that we have. A reflection along line S. This certainly is an answer. Is line R a line of symmetry? The answer is no, because this line doesn't divide it into two identical parts. The bottom piece of the trapezoid is much bigger than the top part. Okay? All right, so let me go ahead and take a look at the other ones. A 90-degree clockwise rotation. We're going to rotate this downwards clockwise, 90 degrees. That will not give us exactly the same image as what we started with. 180 degrees rotation is the same as reflecting along line R. That will not give us the same image because it's going to be flipped upside down. 270-degree rotation will have the image facing the left side. That will not give us the exact figure that we started with. Okay, so it looks like only option B will carry the figure on itself. Now, to help you see exactly why that's the answer, let me show you all the figures that we have. Just a minute. All right, so here we have 5 copies of this trapezoid right here, and I'm going to carry out each of this transformation, and we're going to see which one gives us exactly what we started with. Okay, so the first one is reflection along the line R. So we're reflecting along this line right here, line R. Let me highlight it. Let's make it slimmer. So reflection along this line, line R. Let's see what it's going to look like. So this is line R right here. Now what I'm going to do, watch this carefully. I'm going to reflect this up and down, okay? So I have this cool feature here. Flip, up, down, bam. There goes the reflection right there. Is this the same thing as what we started with? Is this figure the same as that? The answer is no. So we can clearly see that reflection along the line R does not carry the figure onto itself, because you end up with something different. Now, so this is option A. We see that option A is not an answer. Now, let's do option B, reflection along the line S. Okay, so this is a side-to-side reflection. Let's go ahead and do that. So I'm going to reflect this image side to side, left, right. Now take a look at this figure and this one. Do they not look the same? Yes. So we clearly see that reflection along line S which is a line of symmetry carries the figure onto itself. Okay? Now let's take a look at the other ones. A 90-degree rotation clockwise. So I'm going to rotate this 90 degrees clockwise. Watch this. Boom. That's a 90-degree clockwise rotation in the direction of the clock. Question to you. Is this the same as the original figure? The answer is no. It's different, totally different from that. Okay, so we can see option C is wrong. How about a 180 degrees rotation clockwise? This is wrong right here. Option D, let's rotate it 180 degrees clockwise. So there goes a 180-degree rotation. All right, now, is this the same as what we started with? The answer is no. A 180 degrees rotation is very similar to this reflection downward. So this does not carry the figure onto itself because this figure is not identical to that one. And then lastly, we have a 270-degree rotation. Will that give us this exact figure or something else? Let's go ahead and do that. Rotate it 270. That's 90. 180. One more. 270. Something like that. Okay? Is this figure the same as that figure right there? The answer is no. So we see that a 270-degree clockwise rotation does not carry the figure onto itself. The only correct answer is option letter B. All right, let's take a look at problem 3. It reads, the circle with center F is divided into sectors. In circle F, EB is the diameter. The length of FB is 3 units. Okay, so let's go ahead and try this problem out. If you're asked to select the correct expression that represents the arc length of arc AED. Okay, so first thing we want to remember is the formula for arc length. If you look at the options, they are in radians. The formula for arc length in radians is r times theta. R theta. Okay, so we need two things to find the arc length. We need to find r, the radius, and we need to find the angle theta. Okay, so what is the radius here if F is at the center? The radius r is equal to FB, segment FB, and we know what the length of segment FB is, right? It's 3 units as indicated here. Next thing we need is theta for angle AED. So what is this angular measure from here all the way to there? That's theta. What is the angular measure there? Well, we have to break this one down and do it step by step. If you look at the upper semicircle, we have a straight line. This is a segment. We know by the linear pair postulate that the sum of angles on a straight line is 180. So if this is 120, AE is the angular measure that will enable the entire angle to be 180 degrees. Okay, so we need to find this angle first, this piece right here, the angle for arc AE. Okay, all right, so we know that. Let's do the calculations right here. We don't know what theta is. We know that the measure of angle AFM plus 120 degrees is equal to what? Is a linear pair, which is 180, right? So how do we get the measure of angle AFE, not AFM? Where did M come from? AFE, let's correct that. So how do we get the measure of angle AFE? We'll simply subtract 120 from 180 degrees, and that will give us the angle of AFE. All right, let's go ahead and do that. So we'll have subtract 120 from both sides. Subtract 120. Some of you already know what the answer is because you're really smart, and you can just do all this hard math in your head. Okay, AFE is 180, 80 minus 120, that's 60 degrees. So this upper angle is 60, but that doesn't give us theta, okay? Theta is angle AFD, so we need to find out the angular measure down here, okay? So the angular measure of EFD is a linear pair with 45 degrees and 30 degrees, okay? So let's go ahead and figure out what that is. The measure of angle EFD plus 30 degrees and 45 degrees is what? Is a linear pair. How many degrees in a straight line? 180 degrees. Okay, so to get EFD by itself, we combine these two. Measure of angle EFD, 30 plus 40 is 75. We're going to subtract 75 from both sides, so we know what the measure of angle EFD is. So if you subtract 75 from both sides, we're going to have, let's go ahead and do that, minus 75, minus 75, and the answer is going to be 105 degrees. Okay, let's go ahead and put that back in. So the measure of EFD is this angular measure right here is what? 105. Okay, so now what is theta? Angle theta is angle, the same thing as a measure of angle what? AFD, this entire angle AFD, okay? And if this is 60 and this is 105, we just simply add 60 plus 105, and that gives us the measure of AFD, which is 165 degrees. Now we have R and we have theta. We are now ready to find the measure of the arc, the length of the arc. Okay, so arc length, let's write that again. Arc length is r theta. R is 3. Theta is theta is 165 degrees, right? But wait, we can only use this formula when the angular measure is in radians. So what is 165 degrees in radians? We have to convert this into radians. So to do that, we're going to multiply 165 by a conversion factor, okay? So we have 165 in radians. We are going to multiply 165 degrees by pi over 180 degrees. That converts our degree angle measure into radians. All right, so let's go ahead and simplify this. So we're going to reduce, so let's go ahead and do that. How do we reduce this? Let's reduce by 3. Oh, we can reduce by 5. 5 goes into 165. How many times is 5 going to 165? 3 times. It goes into 16 3 times. Carry 1. 15 3 times. 33 degrees. And then 5 goes into 180. 5 goes into 18 3 times. Carry 3. 5 goes into 36 times. We'll multiply across. We'll have 33. Oh, the degrees cancel out. 33 pi over 36. Can we simplify further? The answer is yes. We can divide top and bottom by 3. If we do that, divide top and bottom by 3, we'll have 11 pi over 3 goes into 36 12 times. So what is this? This is theta in radians. Theta in degrees is 165, but in order to use this formula, arc length is equal to r theta, we need to convert our angular measure into radians. If you look at the options we have here, there are no degrees. That's an indication that we're to convert our angle to radians, okay? So now that we know what r is, let's multiply by, we know what theta is, let's put it in here, 11 pi over 12. Okay? Multiply across, we have 33 pi over 12. Wait, we can reduce. Divide top and bottom by 3. Okay, divide the top by 3. Divide the bottom by 3. And your final answer is 11 pi over 4. So option letter B is your final answer. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you have any questions or comments, feel free to include it in the comments section below. And also feel free to subscribe to our channel for the remainder of this review series. More clips can be found on mathgotserved.com. Thanks again for watching and have a wonderful day.